There's a lot of biblical references to mustard, but nobody ate it.
Okay, welcome everyone. Just wanted to remind everyone that in 2 weeks we are having 20th year anniversary of the Institute for Theory and Communication. So that's a new and unusual event. We decided after 20 years that we should celebrate because we have such great postdocs passing through this place, and some of them were not here for 2 decades. So they will be here in 2 weeks, and I highly encourage anyone interested to register. You need to put your name. There is a link, and then Jacqueline and TJ can help you if you don't find the link. Tomorrow the registration closes because we need to know how many people show up for given the size limit on the room and the food that we have to sell. So please do it by tomorrow if you're interested. Everyone from here is encouraged. It's open and it will not cost you money. And so today we have 4 exciting talks. I see. Okay. My list here shows Rosanne Stefano speaking about alt text, but I see Alice really speaking instead.
Yeah, it's like a.
So hi.
Okay,
Right.
Let me just mention the other speakers before we start. Then we hear from a sabbatical visitor that used to be a postdoc here, Mikhail Medvedev, who is a professor at Kansas, the University of Kansas, and he will talk about on zebra radio emission of the crab pulsar, solving a puzzle that is 15 years old, and only Misha can do that. And then we'll hear from Walter Golay from Harvard. Where is Walter? Over there. Who will tell us about time-lapse VLBI imaging of the closed active binary HR 1099. He will tell us what this. And finally, Thomas Pfeil from CCA, from New York City. Where is Thomas? Yeah. Who will tell us about how dust grains influence the weather.
Can you hear me, Allison?
In protoplanetary disks. So anyone worried about traveling there and worried about the weather, you will hear all about it. Let's start with Alison and Rose.
Right, yeah, surprise. Kim, can you hear me now? No, she can't hear. Okay. Well, we're having some technical things, but we can hear you, Kim, so just 1 minute. So Rosanne was supposed to join by Zoom. She's clearly in another Zoom room. So we've sent her a link. Hopefully she'll join. But I'll just give a very quick introduction. So Rosanne wanted to talk about alternative text, which Kimberly is going to give a presentation on. But she wanted to just give a quick overview of the EDIB committee, the Equity, Diversity, Inclusion, Belonging committee that Kim, Rosanne, and I are a part of. And she wanted to just make you aware of that and some of the things going on. She wanted to introduce the Lights On project, which I run, which was a solar eclipse sonification tool for the blind and low vision. We built 900 of these devices for the past solar eclipse, and we were going to give a quick sound clip of that, and then Kim's going to jump into alternative text, because we don't possibly have time to talk about everything right now. So let me see if I can get Kim to do that, and we'll focus on the alternative text. Sorry for the technical stuff.
way, she's muted, or you're muted.
I'm muted. Can you hear me, Kim?
Yes, now I can hear you. Yep.
Sorry, I just trying to give a quick introduction. Rosanne, this is Zoom. Can you play the quick sound clip and then you can jump into your presentation?
Absolutely. That sounds great. Let's see.
So this is just a quick demo of what you might expect during a solar eclipse.
All right, hopefully you can hear this.
You can unmute yourself so she knows.
So in bright light, it's a high flute sound, and then it kind of glows into a clarinet, and then a low clicking during totality. So this would be like the absence of light during totality, and then we come back out during. This is a very sped up version of what you might expect.
All right, let me launch again. So hopefully my volume is good. All right. So I'll try to be brief, but I wanted to give a quick overview of how we're working on creating rich visual descriptions of astrophysical data here at the CFA. The project that I started on was for the Chandrax Observatory. A few years ago, we started working with some subject matter experts in visual descriptions who are also members of the blind and low vision communities. And we started creating a rich visual text for every image that we released from the Chandrax Observatory. So in real time, as soon as an image came out, there was a verbal description of these high energy astrophysics data sets. And we provided those in multiple formats, in text format and audio format, in shortened alt text format, because you can only be allowed so many characters for short web alt text, as well as including in metadata and whatnot. So this is just a quick example. I won't read it all to you, but I'll put in at the end of the chat a webpage where you can read some of these visual descriptions for yourself. But there are some sort of key things that we're doing with these visual descriptions. For the first, we're describing the image as it appears, but we are adding explanations of the scientific phenomena. And it's really important to do both of those things together to coordinate both the visual appearance, but also the scientific information into one short text package. And then the second key strategy is that style for these is pretty important. A lot of these are run through readers for people who are blind or low vision. And so having short sentences, having frequent commas, and using proper nouns instead of referring to it, for example, all really helps the listener as they're building their mental map or their model of what this object might look like. So minimizing that word it and keeping the object name in it, whether it's Quasar 29743, and using short sentences that have built-in pauses with those commas or with a lot of periods, so that as the reader is processing through it, there are those natural moments to be able to absorb the information. And why do we take this approach? Well, we tested this with people who are blind or low vision, but we are also sort of basing it on the art world's use of descriptive labels that they've been using for quite some time. And this piece of artwork that we have on the screen right now, you could catalog how many dogs are at the poker table. But if you're an art historian, you might also add a little bit about the artist, the historical period that it was situated in, the Provence, right? So having that background or extra information, the storytelling around just the visual, helps situate the listener or the reader a little bit easier. And we do the same thing for astronomical images, whether they're Chandra images or other types of multi-wavelength images. And the basic how-to is that when you're describing these scientific images and you're kind of helping showcase some of that sciencey goodness that's captured inside them, you want to make sure you very briefly explain what the subject is. You want to very succinctly say why it's important, and then you want to describe what it looks like. Those are kind of those three key points. And this is an example of how we've done this for supernova 1181. We'll talk about it of being a supernova remnant. What is that? The remains of an explosion that happened hundreds of years ago. What are we seeing? This bright multicolored spherical nebula, etc. And then we go in and talk about it, threading in more science as useful, and talking about the various visual elements. So a few tips on this are, first, to be concise. What we found actually people really love when we're able to sprinkle a little bit of the sort of poetic nature of these images. What you're trying to do is sort of liken it to the experience you get at looking at it. And there is a certain amount of beauty and awe in an astronomical image typically. So being able to sprinkle in a little bit of that poetry while being not overly verbose is really helpful. And again, keeping those short sentences. So the example being the red ring features a tangle of fine lines encircling a black disk. Next sentence, this is, et cetera, versus trying to all list that as one long clause. Using those proper nouns, again, super important. It's really difficult for people, particularly a non-expert user, to be able to remember what the name of the object is or what it is we're talking about if you're constantly using an it, a they, a that, whatever it is. So making sure you're really weaving in those names and giving that explanation when you can. And then again, as I mentioned, connecting the visuals with the elements of the phenomena itself, right? So if you're talking about a quasar, you're going to be referencing that. If you haven't defined even what a quasar is, and it's a non-expert audience in particular, just take a little moment to do that. Making sure you're talking about what it is you're looking at is really useful. And a lot of people ask, should color be described or should it not be described? If it's for somebody who's blind, for example, they might not have a history with color, but it's still actually very important to incorporate color into your descriptions for multiple reasons. The first one is that there is a huge spectrum of people who are considered blind and low vision, and some people will have color information. But also, even for people who are blind from birth, they have a sort of cultural awareness of color. So even to someone who's blind, the idea of something being red can typically give them some of that information of immediacy, of like a stop sign, for example, because they are provided that information as they are going along. So having that kind of color information is very helpful for people who are low vision, but also can be helpful for people who are blind as well. And again, punctuation is really important as well, because it just adds a little bit of pacing, I guess I would say, to the text itself as it's being read by a reader. But the one main takeaway about these visual descriptions that we have done a lot of testing with people who are blind or low vision on them is that any sincere attempt to create good alt text is better than nothing for those audiences, right? Even if what you think you're going to write is not going to be amazing, it is going to be amazing for somebody else who is not being given the opportunity to use it or to access it in any other way. So even your worst version of alt text, which I'm sure would still be perfectly fine, will be very useful to somebody who's trying to access data in a new way. And it doesn't have to be poetry and it doesn't have to be perfect, but being able to provide your best attempt is really good, particularly for somebody who doesn't have access to it any other way. The other thing that I would just say as well, first, I need to give a shout out to the whole team that we work with on visual descriptions. It's just been an incredible project to work with. We've heard over and over from the community how valuable it is having these descriptions more than any of the other types of data accessibility products we work on, because they are real time, because they are immediately available. And so that brings me to the idea of writing papers. Even when we're publishing papers in our group scientifically, we still try to attach as much alt text as possible. Different archives are handling this differently still. And from what I understand, the archive.org is trying to incorporate the usage of Word documents into their system in the future, so that having alt text provided that format would be great and be much more helpful. PDF formats are a little bit problematic for the blind and low vision community, so having an additional format of a paper available, such as just a Word doc, is really great for their types of accessibility, and being able to attach visual descriptions right into your captions is another thing that we've been doing and found that has been very, very helpful for the community. So I didn't notice what time I started at, but I feel like that's probably it. I think I'll toss it over to Rosanne to see if she has anything final to add.
No, I want to thank you for that. I'm really honored to be here with these two members of CFA's Accessibility Committee. Allison, did you have a chance to show the eclipse? Excellent. Well, really, I have nothing to add except that I'm so pleased to see that we at CFA are going forward with projects like this, and this one in particular, which can help us to share the wonders of the work we do every day with a wider community, particularly those who are blind and visually impaired. So I apologize for the technical issues that did not allow me to be here at the beginning. I had wonderful introductions prepared. Did you have introductions?
I think Allison introduced me. I'm not sure because I couldn't hear at that point, but it's all good. We're fine. We're all happy.
Okay, well then if Allison introduced you, let me just introduce Allison. You may have seen her last in the national media because in addition to running the Science Center telescopes and labs, she is the lead for Sight Sound, which is a project that created over 900 units to convert the light variations during this last solar eclipse into sound. And 900 units were distributed along the path of the eclipse. And that did exactly the type of thing that Kim has been talking about, making a very important astronomical phenomenon accessible to a wide range of people, some of whom may be our colleagues in the future, and some of whom may even be our colleagues now. So thank you very much. And I'm afraid I only got to hear the end of Kim's talk, but I really enjoyed it. Thank you, Kim, and thank you, Allison.
Can you unmute so they can hear us? Okay.
Yep, we're
Any,
unmuted now.
any comments, questions to what we heard? Yes, please go ahead.
One question, I don't know how well they can hear me, but I was really intrigued by the suggestion of incorporating the scientific content into the description. And I know there's a balance you might want to achieve between objectivity in the description versus interpretation that you're injecting. Is there any guidance on that, or is there a demand from some parts of the community to sort of get more of an objective description with less scientific interpretation? Like, this is from emerging binary, supernova versus what you're actually just observing.
Hope you heard that, Kim. Did you hear that?
I did hear it. I did hear it, actually, yeah. So obviously these, none of these communities are monolithic, and they're very diverse communities in and of themselves. But the various communities that we've worked with on this project for various kinds of testing have all pretty much underlined the idea that when you go to a museum, there is some interpretation in what you're seeing, and it helps the reader to understand it because they're not an expert in that topic. And that approach is something that they're used to and something that they seem to appreciate. Again, that's not speaking for every person who is blind or low vision, but all of the people that we have worked with in our testing have essentially been saying the same thing. And so for us, what we found is pretty quickly, we found that just describing, the name, rank, and serial number, particularly for somebody who is not an expert in the high energy astrophysics arena, right? That did not provide enough information for them to really intuit much about the object. You can say this is a duck in a pond, and that is still better than nothing, I would add. But if you can talk a little bit about this is an older duck in a pond, and there are 5 ducklings passing by, and they're in this pond because it's spring. Whatever the information might be that you have to impart that provides that contextualization is something that is typically appreciated. Now, of course, you do want to stay succinct. You don't want these to be, 2-page essays on what the visual is, but trying to maintain a balance of getting the true visual description in that'll help the listener create that mental map, right? So like the image behind me, you want to talk a little bit about those concentric rings. You want to talk about some of that filamentary structure. You want to talk a little bit about the color. You want to talk a little bit about the overall sort of dynamic nature of what it is, and, wrap that through with a little bit of that description on some of the coolness of it, if you will. I don't know if that helps, but that's kind of the approach that we're taking, again, based on who we're working with in our testing audiences.
People are attracted to stories, so that's important to mention.
Yeah, stories are very much appreciated. Yes.
Let's thank Rosanne, Kim, and Alison for being.
Of course, the colors are false colors. Well, yeah.
Hello, everyone. Can you hear me? Wonderful. So what I'm going to talk about today is some interesting story, really, about the 15-year-old puzzle related to the radio emission from a crab. And a little bit of a reminder of a crab. Of course, we all know what it is. It's a pulsar located in the Crab Nebula. This pulsar in the nebula is about 1,000-year-old, and the pulsar itself is a magnetized neutron star with a field of 212 Gauss or so. It's spinning 30 times a second roughly, and is located about 2 kiloparsec away from us. The light curve of a pulsar, is represented by two peaks, the main pulse and the interpulse, and they are seen practically at all frequencies, starting from the radio and ending in high energy emission, X-ray, and even gamma ray. The individual episodes, of course, are shorter than the average profile of each pulse, and nowadays we're actually doing this analysis, well, not we, but I mean we as the community, but of course observers do that. Observers are really amazing here in terms of what they can do. They perform temporally resolved spectroscopy, and the temporal resolution is down to the nanosecond basically, and the spectral resolution is great and is essentially determined by the temporal resolution. We hit the hard limit here, whichever we want to explore better, the temporal resolution or the spectral resolution. And all the typical emission episodes, and here is one of them from the main pulses, they last for a few microseconds. Themselves, they consist of a number of individual subpulses, probably blended. And the main feature of all of those events is that they are broadband. They basically cover the observational band for those observations. All of them except just one beast. And this beast is the high frequency interpulse. It starts at about 5 gigahertz and extends down to, or up to 30 gigahertz. That's where the observations stop. Maybe it's extending further down, further up. It has a remarkable and really strange property, namely that the spectrum is represented by the emission bands. That's a very peculiar thing. I mean, there are not so many mechanisms which can give you a striped emission in the first place. One can think of harmonics generations, for example. That would be fine if the separation between those bands is constant. Then it's going to be just the harmonic, and each band is multiple 1, 2, 3, n times the fundamental harmonic. But this is not the case. One can plot the separation delta omega as a function of the centroid of the band, and it appears to be a nice line with a factor of about 6%. To be precise, delta nu is 0.057 times nu. That's of extremely high significance, statistical significance. If you just count how many those stripes are going to be appearing in the observational domain, it's about 30. It's a lot. And we don't have any mechanism at our disposal, the emission mechanism, that can produce the proportional separation. If you know one, please let me know. I'm not aware of that. And people have tried, but for 15 years, first observation is 2007, for 15 years there's been a number of attempts. And there are papers written on discussion of individual models or comparison of the models, but none really works. There is another, actually there are several properties which one should take into account as well. First of all, those bands that I've shown always exist. It's not an intermediate phenomenon that appears and disappears. They exist in every emission episode of the high frequency interpulse. There is not a single one that doesn't show that. There is a little bit of excess of dispersion measures, so probably there is some plasma intervening along the line of sight, longer line of sight maybe, the light path to the emission region than the main pulse, for example. The pattern, the positions of individual stripes, they can change, those positions can change on a pulse-to-pulse basis. That's not surprising because the system is very dynamical. What's surprising is that sometimes in the observations of such episodes, such moments, some epochs, I should say, when they stand still and don't move. What's shown here on the left is this pattern basically persistent for the day of observations. That's the day of observations. 2.5 million cycles, rotation cycles, and they don't move. It's 100% polarized emission, and the position and angle doesn't change. It doesn't change within individual pulses. It doesn't change from a pulse to pulse. That's really strange. And any successful model, and we don't have any until what I'm going to present. I hope it is successful. The model should explain all those features. And we propose its diffraction. So there is some source behind the pulsar itself that lights up the magnetosphere, the pulsar, and this pulsar blocks the light, and what we see is the fringes. We're at a given position, so theta is a constant here, and omega is changing. You have fringes at different omegas. We have the minima and maximum. Well, if it's that simple, people should have come up with that before, right? And they have, actually. And that's been ruled out immediately, because the intensity is proportional to the sine squared of this x, which contains omega. Sine is a periodic function, which means omega is a periodic. If you change omega, you have intensity being at periodic intervals. So it gives you stripes which are periodic. In other words, the distance between them is a constant. And here we have a proportional scaling. So it doesn't work. It actually does. There is one thing that one should remember. It's not just an obstacle. It is an obstacle with magnetic field and plasma in it. And if you have the source on the left somewhere beyond the light cylinder, and actually that's a normal mechanism for normal place to produce radio emission for the crab, unlike many other pulsars where the polar emission actually is dominating and producing the light. Here we believe that it's the emission from the outskirts, from beyond the light cylinder, and associated with mergers of plasmoids which appear due to the connection in the current sheet. There are reasons for that. I'm not going to go into that. And the point here is the following. If we have plasma with magnetic field, and let's consider an electromagnetic wave propagating through such plasma. It has two different polarizations. It can be decomposed into two different polarizations. One in which electric field in the wave is along the B, and therefore this wave doesn't feel magnetic field. It just propagates it as if there is no magnetic field. It just feels plasma, but that's it. The other one is with E perpendicular to B, and this one feels magnetic field, and its dispersion is complicated. So it's the O mode is the first one. The second one, which feels the magnetic field, is the X mode, and we know that X mode is heavily damped in the magnetosphere. O mode is not. It doesn't feel magnetic field. It propagates as it should, and in the plasma even without magnetic field. And the only thing that appears in the dispersion is the plasma frequency. The wave doesn't propagate in the region where its frequency is less than the plasma frequency. So if you have a changing density, a wave is going to be reflected from that region of higher density. Actually, it's the very same thing with metals. Metals reflect exactly for the same reason. We have lots of free electrons, and the plasma frequency inside a metal is smaller than the frequency of light. And therefore, we have this gradient of density. Therefore, the region that is seen, that's illuminated and looks the light, is actually a function of frequency. So for high frequencies, the blocking screen is bigger. For lower frequencies, it is smaller. So this A, which is the shield that blocks the light and produces diffraction pattern, is actually frequency dependent, and we can break that constancy of delta omega and make it proportional. And that's basically it. Everything is shown over here. I'm skipping the math here. It's not a math class here. I'm giving you the result. There is a free parameter here. Actually, I have to go one slide back. There is a free parameter here, M1. M1 is the number of the fringe at the lowest frequency that we observe. In optics, it's called the fringe order. And this is not known because we don't know which fringe we see. That's the only free parameter in the model. And we can see how our result is changing if we change that parameter. And apparently, it's not that dramatic. If M1 is sufficiently large, greater than 100 or 150, it doesn't really affect the result that much. How big that number can be? Well, we have at least 30 fringes that we actually see. So M1 cannot be smaller than 30. It's a very natural thing to assume it is maybe 10 times bigger or maybe even larger than that. So 100 or 150, the number for M1 is completely natural. We don't expect that we see just a specific end, higher end or lower end of our fringe distribution. We see something inside the big region, right? And this allows us to basically get rid of this M1. But this uncertainty in M1 results in the uncertainty in the deduced density of plasma in the magnetosphere. And you see here it is plasma density, electron density if you like, is proportional to R to some minus alpha. And alpha is around 2. It's a power law. And I'm a theorist. You can guess, well, I assume that it's a power law. No, I didn't assume it's a power law. This power law is deduced from observations directly. It appears to be a power law. I didn't make any assumption here. The only assumption here is that M1 is large. That's the only assumption. So we actually can reproduce, we can deduce the density in the magnetosphere. We can make tomography of the magnetosphere of a neutron star. How reasonable that is? Well, the smallest frequency versus the largest frequency, they diffract at radii which differ from each other by a factor of 6. Plasma is present in the magnetosphere, and the lowest possible is so-called Gall-Dirac-Julian density. That's required for the magnetosphere to rotate as a rigid body. It means in these numbers, in these definitions here, m is equal to 0. This is multiplicity. So it basically, multiplicity is how much we have, how much more plasma we have compared to the minimum needed. Of course, the minimum needed is m equals to 1, and in this case, this diffraction at 30 gigahertz is going to be close to the neutron star surface. But if we have a larger plasma density, larger multiplicity, then it's going to be further away from the neutron star surface. How big? Well, on the closed field lines, m, the multiplicity is around 10 to 100. On the open field lines, it's 10 to the 4, 10 to the 5. That's what simulations show. Everything is within normal parameter regimes, I'm not really even stretching the numbers. They appear to be that way. One important thing, though, is if we keep increasing the frequency, we go down closer and closer to the neutron star. So at some point, we have to hit the neutron star surface. As we approach the neutron star surface, we're going along this line toward, toward larger delta omegas for larger frequencies, right? And that's where we stop. No observations exist beyond 30 gigahertz. That's what's observed. What if we go beyond? We should follow the line for some time until some critical frequency when there's diffraction. Diffracting magnetosphere size is going to be the size of the neutron star itself. And it cannot get reduced any further because it's a hard surface. So beyond that, at higher frequencies, it's going to be a constant. Delta omega is going to be constant. A normal diffraction pattern from any standard obstacle. So this is a task for the, I hope, forthcoming observations with submillimeter array and maybe ALMA. Of course, sensitivity matters here, but if we're not too far from 30 gigahertz, I think it is still possible to do that. And it would be remarkable, because if we do that and we find this break frequency, then we can immediately deduce not just the power law index of the density, but we can actually deduce the actual density, the normalization of the density at the neutron star surface, plasma density at the neutron star surface. And we can recover, therefore, the entire distribution of plasma in the magnetosphere. I think it is totally remarkable. Given the size of this thing, we're talking about Event Horizon Telescope, right? And that's the size of what? Million times bigger than the neutron star itself. So using the same technique, essentially, right? The fringes, the interference, we can actually get a handle of on the physical parameters of an object which is just 10 kilometers across. That's just a statement here, basically, that we've done a little bit better than that. We're not just proposing theory. We actually try to simulate things because there are certain assumptions from the theoretical point of view. For example, the thin screen and the dependence of the refraction index is a function of position, as a function of radial distance from the neutron star surface, and actually things work. Basically, what we've done here is we've performed simulations of an electromagnetic wave going through this refraction index shown over here, radially dependent over here. Of course, it's two-dimensional simulation. And we reproduce the fringes, and the fringes appear to be in the right place. Of course, this is a model problem. And that's the end. That's conclusions. We have, yeah, that's a nice figure, actually. That's what the AI is good for. I think theory is still there. We can do better than that. So the model explains spectral emission bands, the existence of the bands at all times, the proportional separation, the pattern that stays for a long time sometimes, the highly polarized emission, because we're dealing with just one polarization, the O mode. X mode is damped, as I said. The constancy of the polarization angle, of the position angle of polarization, linear polarized light. Well, why? Because you always see the same configuration, geometrical alignment of the source, the magnetosphere, and the observer. The X is dispersion measure. Well, it's obvious because the light is actually the radio light is going through the magnetosphere. And actually, it's not just speculation. We checked that the numbers, the dispersion measure actually works as well. And I didn't say, but there are two high-frequency components. They can be interpreted as the reflections of the magnetosphere as well at different rotation phases. And we have this suggestion for future observations. I think this is a really interesting thing to do. And I don't know how difficult it is, but I would really try to do it if I'm an observer. And yeah, we have a better understanding of the pulsar is and the environment of the pulsar. Thank you.
Thank you, Misha. Just a footnote then. You didn't mention gravitational lensing, but it could be quite significant near the neutron star. Are you making corrections for that?
No, we're not making corrections. That's a nice suggestion. Actually, I have to look into that. Yeah, thank you. Yeah, good point.
Any other comments? If not, let's thank Misha again.
All right, hello, can everybody hear me?
Yes.
All right, hi everyone, my name is Golay. I'm a first-year graduate student here at the CFA, and today I'm going to be talking about a project I just finished up with my undergrad collaborators, looking at the close active binary star HR 1099 using the VLBI. So first, what is HR 1099? This is one of the classic RSCVN stars, which falls under this category of a chromospherically active binary. So what does that exactly mean? They're broadly unified by at least one evolved later type star, and then that has some evidence of enhanced magnetic activity. What exactly that means, there's a lot of different definitions, but in the case of RSCVNs, a lot of their variability, not in this case here, you're seeing the original RSCVN where it's eclipsing, but the variability from year over year in the light curve actually comes from large photospheric spots, which have since been revealed using the technique called Zeeman Doppler imaging, which is this really cool technique where you can actually map the surface magnetic field of a rotating body. And people have done this for stars, and in particular, I've done it for HR 1099 at this point. It's been about 30 years, so we don't really have recent data for this particular source, but ZDI has revealed very strong magnetic fields on the primary star, which is the more evolved star, and then the secondary star also has a weak magnetic field component that is detected through this technique. So why are we interested in observing this source? Well, if you look at the period, it's only 2.83 days, and if we know the distance to it, which we do from Gaia, we can actually predict what the separation of the two stars is. And 0.86 milliarc seconds, that's a tiny, tiny angle, but it is accessible with VLBI. So one thing I've sort of become interested in doing is looking at the history of my sources. And so I first started off with Starglass, which is operated out of the plate stacks here, because I knew that my source had an HD number, where HD being Henry Draper. So I eventually found this source, and I found it was first observed in 1892, HR 1099. But I actually had to go to the original catalog, Washington Double Star catalog, to find the original discoverer, which turns out to be FGW Struve in 1827. And luckily, the Navy has done all the hard work of identifying which entry in the actual paper is HR 1099, which is that one right there that I'm highlighting, number 422. Of course, this is a high prep motion source because it's nearby, so these coordinates are totally off from what they are today, almost 200 years later at this point. Yeah, I know, CD-ROM, that was the other thing I wanted to point out, is the paper was originally detailing a CD-ROM that you could order that included the entire Washington Double Star catalog, which at this point is ballooned as well. And what's interesting is, I mentioned that the separation was 0.87 milliarc seconds. Struve did not see that, obviously. HR 1099 is actually a triple system, and he actually saw the tertiary component, which is almost a whole arc second away. So that's how he discovered it. And of course, I have to give a shout out to ADS because they do such a good job of making this information easily accessible. Okay, so why is radio emission from RSCVNs interesting? Well, first of all, they're one of the only classes of stars that are bright in the radio. So for example, if you were to put the sun at 3 parsecs, the radial sun at 3 parsecs, you would barely be able to detect it, if at all. Which is interesting because the sun has a lot of activity that we do see in the radio. And the thing that we were interested in answering is the possibility of observing a coronal mass ejection on another star. That was the original motivation for this project. But I'll just point out that these RSCVNs, they're very radio loud, and they're unusual stars because they're so radio loud. And the emission is mostly non-thermal. If you look at the low frequency emission, hundreds of megahertz, it's well modeled by ECMI, which is a particular emission mechanism. I won't be talking about that here. They have, moderate magnetic field strengths, a couple hundred times that of the sun overall. And because this is a non-thermal process, the gyro frequency, which we heard about just a second ago, is well described by power law energy distribution for the electrons. And this is what we typically call gyrosynchrotron. We distinguish this from synchrotron because in the stellar case, the magnetic fields and the number densities are well tuned to cause circular polarization. So that's what I'm plotting here on the right. I'm plotting Stokes signs, Stokes V in the top and bottom panels for HR 1099 for a previous work of mine. And what you can see is this source is quite bright. There's the power law gyrosynchrotron model, and then also it's quite polarized. So you can see it gets above 30% in the Stokes V over I, which is quite interesting. And so when we do the spectral energy distribution modeling of our source, we get some estimate for what the volume of the radio emitting region is, which I'll note is quite large. It's almost 3 times the volume of our sun. And we also get some estimate for what the magnetic field should be. But the question that this raises is, okay, where in the binary does the radio emission actually come from? Is it in an interaction region between the 2 stars? Is this purely a binary phenomenon, or is this one star or the other that's responsible? The Zeeman Doppler imaging that revealed the photospheric spots seems to suggest it should be the more massive secondary star, but we don't really know for sure. RCVNs are characterized by the fact that they don't have very much evidence for mass transfer, so would you expect a shared magnetosphere to be causing this radio emission? So these are all questions that we were trying to answer in addition to this idea of potentially observing what you might call a stellar coronal mass ejection. So, and I'll just point out, that's our source. So what do? We looked at it with the VLBI. We did sort of a standard phase referencing experiment. And we looked at the secondary calibrator every 15 minutes to ensure the stability of our positions that we would be deriving. So that's what I'm showing on the right here, is the positions of our secondary calibrator, which is the blue dot down at the bottom, and then our source is up at the top, and our primary phase calibrator is in the middle. So what we do is we nod in between our calibrator and back to our source, and then then again we go check on our secondary, and from this we can reference our positions of HR 1099 and 0340 to our primary, and since we know the position of our primary, we know the exact positions of our source and our reference target. And since our reference target is a known quasar, extragalactic source, it should be stationary over the course of our observation. The spread that we see here is some estimate for what the error is on our position. So what do? We observe this source for 6 different times for 10 hours each, and we plot this in the co-moving frame of the binary, and so that's what you're seeing here. So each color represents a different epoch, and each data point is a position derived from one individual hour slice. And so you can see that there is an ellipse that is well delineated by the radio positions, which is representative of the inclined rotated orbit, the circular orbit of the binary star. And you also see that GCRF3, which is the Gaia-derived position, is offset, which is quite interesting. And this offset is actually very well predicted by what are called the frame linking parameters, which is how we transfer from the radio reference frame to the optical reference frame. Now, what's interesting is if you go to the co-rotating and co-moving frame, you get something like this. So here you can see that the radio positions are all offset from the interbinary region. And in this case, I'm showing it so that the more massive star is the one that has the radio emission associated with it. Now, because the parameter that defines the orientation of the ellipse that's called the big omega parameter. that defines whether the radio emission is essentially associated with the more massive star or with the less massive main sequence star. And since the optical observations could not constrain that parameter, it was a free parameter in our model. And so we had to make some assumption about which star the radio emission was associated with when we were fitting for the orbit of the binary. Now, I will say that one thing we can say for sure is that the radio emission does not come from the interbinary region, which some people have predicted because of X-ray observations, which seem to indicate that there was enhanced activity when the interbinary region was most visible. And there were some arguments for correlations between X-ray flares and radio flares, but this has not been, that was never confirmed, and this definitively shows that the radio emission is persistent over 3 months or so. It's a large loop, and it appears to be mostly stationary in the co-rotating frame, and it's not in the interbinary region. So what we can do is we can turn this into a nice movie. So here is the binary star going around each other, and it's going to pause and slow down at the particular epochs that we observed. So down in the bottom right, I'm showing the beam, which you can just think of as the resolution. And then it pauses and slows down and shows the actual morphology of what the radio emission looks like for that particular epoch in the orbit. Now, like I said, these observations were collected over 6 months. So this isn't one single period of the orbit of the binary star, but rather all of them face folded onto each other. So essentially, we're making the assumption that the radio emission is stationary. So finally, I'll just show, I want to skip this slide because I want to show this one, which is, let's compare to the solar case. So like I said, the sun is a very unique case, as many people in this room study and already know. And so what we were able to do is, since we sliced up our data into individual hours within each of our 6 observations, we were actually able to predict motion or measure motion in the co-rotating frame. So what we ended up with is 5 of the 6 did not have any evidence for motion. However, the epoch that we observed that there was a flare in, there was about a flare of 100 millijansky versus the 10 to 20 that we were normally observing, and that's the green dot down at the bottom. And there's some very weak evidence, 3 sigma, for motion, which is roughly consistent with the median velocity of a solar coronal mass ejection. However, this is very tentative, and how we corrected our data, how we calibrated, sort of changed the significance of this, and so it was right on the edge. So there might be some evidence for energetic particle events on other solar systems, but basically stellar CMEs remain elusive and hard to detect. So what is the new picture? We can do a lot of different things with VLBI observations that don't necessarily have to do with the physics. Like I said, I mentioned frame linking, the optical and the radio. We can do things like that. But this is what the binary sort of picture is for HR 1099 now, is you have a large coronal flare or a large coronal loop that is persistent over many months, even years, goes through periods of flaring, and is located on either one star or the other, but is definitely not in the interbinary range. So that is, that's pretty much what the picture is. And also I'll mention that we do see circular polarization, but it's not actually resolved into 2 different regions. I'll mention this was just published a couple weeks ago. So if you want to read the paper, here it is. You can scan the QR code. And then there's also an accompanying website where if you liked my figures or the animations, you can see how I made them using the code that's posted there. Thanks very much.
Could this shed any light on planets?
Yes, so that's why CMEs are so interesting and important to study, because we have yet, as far as I know, we have yet to observe a stellar CME. And as we know here on the Earth, that is one of the few things that impacts us quite often is energetic events on the sun. And like I said, the sun is a relatively normal star. So if you had an exoplanet around one of these kinds of systems, or any other kind of radiolab system, many of which are M-dwarfs, for example, you might be in trouble. And we don't really know. We have no clue as to what the flaring and coronal mass ejection-like environment is around other stars. And so the search for life has to take that into account.
Thank you. Any questions? Walter? Looks like everything was clear. Thank you for the nice speech.
Thank you.
All right, can you hear me?
Yes.
Good. Yeah, so hi everybody. So today I'm going to talk about a project that I actually did during my PhD. So now I'm at CCA, but before I was in Munich at the University Observatory in the group of Till Birnstiel. And we were also working together with Hubert Klar from Max Planck in Heidelberg. Yeah, the title is maybe a bit weird because the term weather comes in. But what I actually mean with weather in protoplanetary disks is hydrodynamic instabilities that arise from the stratification of the disk itself. And then they cause turbulence and maybe also flow structure formation, like the one you can see here on my first slide. So the reason we're interested in turbulence in protoplanetary disks is, for one, it's really important for planet formation because it causes particle collisions, and also it causes the disk to evolve, but also because we observe protoplanetary disks in the millimeter, we see the dust particles, and we see that these disks seem to have various different levels of turbulence. So here, for example, HG 163296 even has different levels of turbulence between the different rings. And then you observe other systems, like this observation here by Mikhail Medvedev, where you see the disk is really, really thin, the dust particles are very settled, and this hints towards like really, really low levels of turbulence. And so one of the questions that we were interested in during our project was if there are many of these potentially turbulence-creating mechanisms and instabilities that we know of, why don't we really see them in these protoplanetary disks like this particular one? And the instability or the turbulence-creating mechanism we were interested in is called the vertical shear instability. It's an instability that arises because of the hydrostatic structure of the disk itself, which gives rise to vertical shear. So the angular velocity of the gas in the disk is dependent on the height or the distance from the midplane. And that allows gas particles to move up and downwards in these disks, releasing energy. The only other requirement for this instability to be active and cause turbulence is that you have to have very fast thermorelaxation or cooling in the protoplanetary disk. Because when these gas particles enter regions of different entropy, they experience buoyancy, and this basically damps down the instability and hinders turbulence from developing. And this is, if this instability is actually active, this is basically how it looks like. So this is from a bit of an older work. You can see in blue here the perturbations in the disk's vorticity. So you see these mostly vertical flow structures in the blue here. And in the red color here, I show the turbulent stress exerted by this instability, which is typically low to moderate. But because it's mostly these vertical perturbations in the disk, it can move dust particles to large heights from the disk midplane. And this would, of course, change the appearance of millimeter observations. And another reason why the vertical shear instability is really interesting is because it gives rise to large-scale vortices on protoplanetary disks, anticyclones. And these are typically associated to pressure maxima, which collect dust particles. And that also makes it really interesting in the context of planet formation. However, these kinds of simulations, they were conducted for really simplified cooling prescriptions, which is actually what the vertical shear instability is really sensitive to. And in protoplanetary disks, usually the cooling of the gas is done by the dust particles. The disks are composed of mostly of hydrogen, molecular hydrogen, which is a very, very bad coolant. So if there's temperature perturbation in the gas, it can only thermally relax on a short enough time scale if the gas molecules collide with dust particles, which then dominate the emissivity and therefore can effectively cool the gas. And because this is a collisional process, you need inelastic collisions between the molecules and the dust particles. You can also describe it by a collision time scale that I show here. So then you have a dependency on the number density of dust particles, the collision cross-section, etc. And if you figure this out for a typical dust size distribution that you would expect in a protoplanetary disk, you find that this cooling or thermorelaxation timescale is proportional to the square root of the maximum particle size in these disks. So therefore, because the cooling timescale is so sensitive to the dust size distribution, we would also expect the vertical shear instability and the level of turbulence to be very sensitive to the dust size distribution. And so the goal of this project that I'm going to talk about now was basically to see what the effect of the dust coagulation process would be on the vertical shear instability and the level of turbulence. And dust coagulation is basically this process where we have first submicron sized particles collide due to Brownian motion, stick together and form larger and larger aggregates. So they grow and grow until at some point the collisions between the particles become more and more violent, and at some point they don't lead to sticking anymore, but to break up, and that's called fragmentation. So there's like a natural barrier to the growth process. And we modeled this using the dust pi code, which is publicly available coagulation code by Sebastian Stammler. On the left-hand side here, you can see the outcome of 3 of these dust coagulation simulations. So the difference between these 3 lines that you see here is basically the parameters of the coagulation model. That is the fragmentation velocity here. So if we have a large fragmentation velocity, which is this critical parameter that determines the velocity at which particles break up and not stick anymore, you get, of course, larger particles, which is what you see here in the red line. We have about millimeter-sized particles present in the disk. If you have a lower value of this fragmentation velocity, something like a meter per second or so, which is relatively low, then you, of course, also have smaller particles, in that case, 0.01 millimeter approximately. So we conducted these simulations, and then we calculated the respective cooling times of the gas from these dust size distributions, which I show here on the right-hand side. And as you can see, if you have larger particles in these disks, you also have longer cooling times. The reason is because you have lower number density of small particles, which dominate the opacities, and therefore also slower cooling. So we conducted a bunch of these simulations, calculated the cooling times, and as a next step, we basically implemented them in the Pluto code, which is a hydrodynamics code, and ran simulations of protoplanetary disks and the turbulence evolving in them. And these are snapshots of 6 different of these simulations that we conducted. So the most basic version you could have is basically the isothermal case. And here I'm showing radius distance to the star on the x-axis and height from the midplane here on the y-axis. So this is basically a cut through the disk plane. And you see if the disk is isothermal, if cooling is basically instantaneous, you get very strong, vigorous turbulence, which I show here in the vorticity. You get all these tiny vortices, etc. However, if you calculate the cooling time based on the dust coagulation models, you get a really different outcome. And the simulation I want to focus on in particular is this one here that was conducted with the cooling times for the dust coagulation model with the largest particles. So the fragmentation velocity is 4 meters per second, which is still a rather moderate value. And what you can see is the outer regions of the disk beyond about 70 AU show almost no turbulence at all, while the inner region still maintains some level of turbulence. And what we were interested in now is how this impacts the appearance of the disks and the dust distribution within them. So we added a few dust fluids to our simulations, and these plots here show you now the dust to gas density ratio that we got from these simulations. And again, in this upper panel, you can see in the outer regions where you have almost no turbulence, the dust is just settling towards the midplane of the disk, forming this really, really thin layer, while in the inner part, you have still some level of turbulence, so dust is moving around a bit at least, and you get a bit of a more puffed up appearance. So the next step then was, and I'm showing this only for this particular simulation, to have a look at how these dust distributions would actually appear in millimeter observations. So as a next step, we took our simulation data and we fed it into RedMC3D to perform some radiative transfer post-processing using the standard D-sharp opacity mix. And this is the outcome. What I'm showing here is the intensity. So we see the disk here edge on as it would appear at 1.25 millimeters. I just smeared the image here with some generic beam that you can see here as this gray circle. And you see basically what you would expect from the dust distribution before. The inner regions of the disk appear a bit thick because the turbulence is still active there. Dust particles are moved vertically up and down. And the outer region appears really razor thin because turbulence is completely quenched and the dust particles just settle towards the midplane. We compared this to a few analytical models, which you see here. So these are just analytic derivations of the dust distribution in these disks for different diffusivities. And you see the outer regions, they're mostly consistent with diffusivities of 10 to the minus 4, which is a very low value, while the inner regions, where you still have some turbulence, are more consistent with the moderate diffusivities that we've assumed for this model here. Okay, so to sum this up, the vertical shear instability and the level of turbulence in protoplanetary disks is really dependent on the cooling timescale. And because it is dependent on the cooling timescale, it is also very sensitive to the dust size distribution in protoplanetary disks. We conducted hydrodynamic simulations and radiative transfer post-processing and found that indeed, if you have larger particles, larger initial particle sizes, or large fragmentation velocities in these disks, and respectively large particles, you have lower cooling times, therefore lower levels of turbulence. And this could be one explanation why we observe some protoplanetary disks that appear really, really thin in millimeter observations. So that's basically it. Thanks for your attention.
Thomas, obviously the coagulation is a dynamical process, so you might start with smaller particles and then the distribution will evolve to. So I guess are you planning to expand your simulations to include that process of changes in the particle distribution?
Yeah, that's a really good point, because what I just showed assumes a static particle size distribution. Right. We just calculated it beforehand, then fed the static cooling times in the hydrodynamics code. But we have actually already gone a tiny bit further. So this is a simulation where we actually calculate the cooling time in runtime in the hydrodynamic simulation. So it's not really coagulation yet, but it's already like evolving dynamically with the dust. So you can see the dust settles at the beginning of the simulation. That influences the cooling times that I show on the lower panel. And then some sort of vertical shear instability is still emerging. But yeah, this is not yet published, so it's still under revision. The next step would then really be to include the coagulation process itself in these simulations, but that's really tricky. Yeah.
That's good. Comments, questions? Not, let's thank all our speakers today.